In this video, we're presented with a velocity time graph, and we're asked to select all the correct descriptions of what's happening in the graph. So I'd like to get an overview of what's going on before I even look at all the options here. This is a velocity time graph. It's very common to confuse this with a position time graph. This graph is telling you the velocity of an object at every moment in time. So when t is 0, the object is at rest, v is 0. The y-coordinate is 0 there. When t is 1 second, my velocity is positive 1 meter per second. So it's moving to the right rather slowly. When t is equal to 2 seconds, the velocity has increased and is still to the right. The object is moving at 2 meters per second to the right. T equals 3 seconds, the object's moving 3 meters per second to the right. It reaches a maximum speed at t equals 4 seconds, where the velocity is 4 meters per second pointing to the right. What happens after that is not a reversal of direction, because the velocity stays positive. It's plus 3 meters per second, then plus 2, then plus 1. In other words, the object continues to move to the right, but it's slowing down. So let's look at our options. Option A, the object always moves in the positive direction. That's true because the velocity is always non-negative. Option B, the object turns around at t equals 4 seconds. No. If this was a position time graph, that would be correct. And that's why I threw that distractor into the list. Option C, the maximum speed occurs at t equals 4 seconds. Yes, that's true. 4 meters per second, maximum speed. Option D, the acceleration is always positive. That's false. Remember, the acceleration is given by the slope of the velocity time graph. And that means during this first leg, where I have a slope of positive 1, the acceleration is plus 1 meters per second, or meters per second squared. In the second leg, A is going to be negative 1. The acceleration points to the left, if you like, while the velocity points to the right, and that's why we see the object slowing down. So the magnitude of the acceleration was the same, but the direction flipped. E, the total displacement is 0. That's not correct. If it was a position time graph, it would be correct. But my total displacement here would be a positive number given by the area bounded by this graph and the t-axis. And in this case, you can do this without using calculus or anything. You can just count the squares under here to get the area. Every square has a width of 1 second and a height of 1 meter per second. So every little square is a displacement of 1 meter. Why don't we just count them real quick? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 whole squares. 13 by taking those 2 half squares. 14, 15, and 16. So a little bonus to the problem here. The total displacement is actually plus 16 meters, as this object always moves to the right. Starting slow, reaching a maximum speed, and then slowing down again until it comes to a stop. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.